We're going to do now halogenation reactions of alkenes and alkynes. So, halogenation. Okay, when we have an alkene, let's say that we're going to be doing bromination. So one reaction that you will see is, say, bromine. Here, you might see when you're completing products, just bromine by itself. Or maybe you will see an organic solvent such as carbon tetrachloride, a solvent that is not nucleophilic. So what is important of this reaction? You will add the crucial thing here is that the intermediate is a bromonium ion. And why is that important? Because of the say the nature of the product. It turns out that it's found experimentally that the two bromine atoms are opposite side when they're added to an alkene, and that's explained through the formation of a bromonium intermediate. And that's similar to what we have with the mercurinium ion, and I'm going to draw it on the side. When you do mechanical hydration and you want to prevent rearrangement. So this is similar in the structure. So three-member ring, positive charge. So now I did this, so the metal is here. What is interesting here, when you form the bromonium, then you also will have bromide. Then that will attack in this important, in all of these intermediate three-member rings, after you form that intermediate, you will have a nucleophilic attack. In the case of a hydration, if you're doing hydration, then the nucleophile is going to be water. And it always attacks at the more substituted carbons. So this is the attack that you will have. In the case of the bromonium, it's the same. Your nucleophile, if this is a condition, is going to be bromide. And then bromide is going to be attacking here at the more substituted carbon. And why is that important? Because the way the product is, the way the bromines are added. So we need to, if we remember that intermediate, we will know the attack is opposite side. Essentially, if you think this cyclic structure, you will have less steric hindrance in nucleophile if you attack opposite to that. So that's kind of the idea. Here's this cyclic structure having the attack opposite side. But not only opposite side, but so opposite side means anti, and but also the attack in those intermediate with three-member ring and positively charged. The attack is at the more substituted carbon. So let's draw the product. If this was on the top is wedge, then the nucleophile had attack on the opposite side, meaning it will be on dash. So I'm going to do my bromide here. So opposite to that. If this is up, this is going to be coming from the other side. So, and then this will open up. The other bromine is going to end here up. So as you can see, one up, one down. That's anti. Or the mechanism was an anti-addition. So anti-addition. These two bromine are actually trans to each other. And this, you will have that plus the enantiomer. And these two, remember, are chiral center. Each of these carbon will have 4 different substituents. For example, this one, bromine, and each, that's a picture, then the chain and the other chain. So 4 different. All right. So it is important to remember this goes through that intermediate. It is an anti-addition, so the product ends up like that, opposite sides. And the attack is always at the more substituted carbon, similar to that intermediate. Okay, you're adding 1 mole. So let's see what happens when you do the alkynes. Oh, first I need to remind you guys something. If we're doing this reaction with an organic solvent that's not nucleophilic, that is the outcome. But you can also form, for example, halohydrines, or which will have an alcohol or even an ether. Meaning, I can do this reaction with a solvent that is actually nucleophilic. If I do this reaction with water, or methanol, or ethanol, or something else, then the bromonium forms but then the solvent is in much larger amount, quantities, compared to the bromide. So the nucleophile here, instead of being bromide, will be water in this case. So I'm going to draw that. So I'm doing the same bromonic intermediate, is the same. And here's your metal. But now, the nucleophile, instead of being bromide, is going to be water. And this will open up just the same. The product here will be, and notice the attack at the more substituted carbon. And that's important when you're predicting products again, because you need to watch where you put in the OH. So if this was your intermediate, the OH had attack, opposite side. So I'm going to put the OH here, which means the metal is here. And then here you will have the bromine. Again, this is opposite to that. So it is an anti-addition. Then remember, what is it you're looking at? If you have a nucleophilic solvent, then you will have that. You can have this, or you can have methanol or ethanol or even an amine. Okay, so what happens with alkynes with that? So alkynes will undergo bromination reactions as well. So let's draw an alkyne here. Let's do. That's a terminal alkyne. So I can do, say that I use only one equivalent. If I do bromine here, then I will add bromine. All right. If I added 1 mole, I can have this. And it's actually major, but you could also have the other product. But this is if you use, say, 1 equivalent. These are the 2 metals. That's major. Or you can have this. Oh, that wasn't a metal group. There's only 3 carbons. 1, 2, 3. So, yay, that's 1 metal. All right, that outcome. If you use an excess of bromine, then you will add twice. So you will form a dihalide. But this is still with a double bond. And here, excess of bromine, you will add bromine. So bromine. So we have 3 carbons, right? And bromine. Okay, so what is interesting is that when we have alkenes and we do the bromination, let me do let's do this alkene. If I do the bromination over to that alkene, I will add to bromine here, of course. I'm going to add bromine and bromine. This is a dihalide, and this is used to synthesize alkynes using an excess of sodium amide. So that's what's important here of that addition to alkenes. And what this is when you use an excess of sodium amide, you will have, say, 2 consecutive E2 reactions. For that to happen, you need 2 halides that can be vicinal, so next to each other, or geminal, attached to the same carbon, to synthesize an alkyne. So here, you're going to go back to this alkyne that I had here. So in excess, and for example, if you had, I'm going to have here, you're going to have an H, for example, here. And then that base, just 1 E2 mechanism. Get in that, form a double bond, that will depart. And that's 1 elimination, and you need to do a second one that will form the alkene. So when you do that in excess of sodium amide, you get an alkyne. So this is how we are connecting all those reactions. So again, alkenes what's important to realize here, we need to figure out the reaction always will go through bromoning intermediate, but what's the nucleophile? If you're doing just halogenation, then it will, when you're predicting process, it will either not showing a solvent or give you an organic solvent that is not nucleophilic. So the attack on the bromonium would be by bromide, and that would be at the more substituted carbon. Those attacks at the more substituted carbon are seen also in other intermediates that are similar. This intermediate with the cyclic three-member ring and positively charged, such as a mercurinium, the attack will be at the more substituted carbon. Now, if you're using a solvent other than that is not organic, that is nucleophilic, such as water or methanol, then instead of attacking with bromide, you will attack with that solvent because it's a larger amount. But the product is also anti. But you need to pay attention that the nucleophile attacks again at the more substituted. So where you put the OH is going to be crucial here. Okay, so in the case of alkynes, you can also do halogenations. If you control that by using just one equivalent, you will get the halogenated alkene, that's a major, or in excess, oh, I forgot here, a number 2. So in excess, you will form you will add 4 dihalas. And we can synthesize alkynes from alkene. If you do one halogenation, you like that, like this, you form a dihalide here. You can synthesize alkynes by using an excess sodium amide and do 2A2 elimination reactions to do that.